Hello again. Alright, first video of the day is up, and I'm going to go ahead and work on the second, or part 6, which will be part 6 of our video series. This one's going to be a little bit shorter, but a little bit more direct and very, very acute points that need to be made in this discussion. So, as we're going along, we're hitting different topics to try to get your head wrapped around each kind of little thing that we're discussing, just one bite at a time, one section, one bite at a time. And this one that we're going to talk about now is about breakering disconnects or fuses. And this one I'm going to do another disclaimer. I know my first video was a disclaimer basically saying that you are responsible for anything that you do, and my information is shared with you, and that you are to verify it. You're on your own, but I'm going to share as much information as I've got with you, and you are in full responsibility for what you do with that information. That was the first video. Well, this one is going to have a little bit of a straight to the point disclaimer. Breakering disconnects and fuses, and this is a disconnect or a combiner box that has some breakers in it. We're only going to talk about concept, not necessarily get too much into details of it. We'll bounce around a little bit of details so that you understand the concept. Hey, buddy. But here's the thing. As I gave you in the last... what you doing, buddy? Say hello. He's my scaredy cat. He's my scaredy cat. As I gave you in the examples of the last video, part 5, you saw that for my battery system that handles my radios, antennas in the radio cabinet right there. There's four GCs in there, 2 strings of 2. So there's added up from 6 volts to make 12 volts nominal system, and then we've got an extra 2 in there just for added ampage and amp hour ratings so that I can run them. But what you saw is this panel is directly wired to that charge controller, and then from the charge controller directly wired to the batteries. There were no breakers or fuses or disconnects in that system. And this system we do. We have, when that sun's come out, and boy is it hot. We have breakers, disconnects, and whatnot in interrupting each one of these components. So remember, we've got the 4 components, right? So in those 4 components, you got the solar panels, you got the charge controller, you got the batteries, and you got your inverter. So whenever you have a series of components like that require, for the purpose of safety and for working on and many other purposes, require some protection for you and for the system components. You need to, you hear me on this, you need to install disconnects and breakers, okay? It's just that simple. Now, how do you need to? This is the disclaimer. I don't know where you live in this world. I don't know what your regulations are in the particular area that you're at, or what you are going to inevitably be able to handle as far as knowledge and the ability to manage your system and components in a safe way. I don't know how smart or stupid you will be. So I'm going to tell you, you better make sure that you get it right, because this is safety. Because here's the thing, once you start adding panels and you start getting a whole lot of these numbers into a higher number. And we're not talking 12 volts and 1 amp, but we're talking 100 volts, and 10 amps. Now we're starting to talk about enough current, enough wattage, that it can physically do you harm if you were to accidentally misappropriately handle it, or you short it out, or you shock yourself. Okay? So this is safety. These things are put in here, and there's mittens. These things are put in here for safety, not only for you but for the equipment, because equipment isn't designed to be connected and disconnected hot. Now, I'm going to tell you what I do, but that doesn't mean that's what you should do. And what I do is I know roughly about where I've accidentally been shocked and what my particular body is capable of handling in the way of current. Not necessarily everybody is going to react the same way, but I know what hurts and what you can't feel, or what's not that big a deal. And for me, I know my tolerances, and that generally runs clear with most regulations. They're similar, but how does that apply to putting a system together? Well, let's just put it this way. There is a safe level of power, and there is a not safe level of power to be handling without some form of protection. For me, I kind of came to the determination of anything up until we get to one panel. Once you get above one house panel, that's when we start to have issues. Now, some code somewhere might even go less than that as far as requiring breakers or not. What I would suggest is anytime you get to a house panel, in other words, if you have a 100-watt panel, 100 watts is not enough to really do you significant harm unless it's the perfect conditions and you happen to be of weak system, and I can't determine that for you. So if you were to take that on the right day, full sun, and you had good contacts, and you ran one contact through one finger on one hand and another contact through the other finger, and you created a loop through your body, 100 watts might be enough to knock you on the ground and stop your heart. Now, I haven't had that. I could feel it and it tingled, but it didn't do that to me because I screwed around with it, and I challenged myself. What does this feel like? I wanted to know. But it didn't hurt me. It might hurt you. I don't know. But in general, when I've been working for systems for other people, anything that's smaller than that, I generally don't worry about any breakers or disconnects unless I'm wanting a switch, something that I can turn it on and turn it off with. Because in doing some systems, I've done quite a few of these where I've taken a single 100-watt panel and used it like I'm going to do. I've got another one of these I'm going to install in my greenhouse when that gets built. And then in that greenhouse, I'm going to do a direct connect to a fan, a ventilation fan to keep the air moving in there. And that does not need a breaker. The sun comes out and it starts moving. You going to sit down while I'm chatting, little one? So for me, it may not be for you. Big disclaimer, I'm not going to be anywhere near responsible for where you decide to put this. What I am going to tell you is don't be stupid and skimp. So anytime you get to a panel, a house panel or bigger, that's when you seriously want to start looking at putting some kind of disconnect between it and the next device. Your charge controller of some form, and then subsequently throughout the remainder of the system. The other aspect of that is on the other end when your battery voltage starts getting up like that. So you may have a 100-watt panel, and from the 100-watt panel to the little charge controller to the batteries, you don't put anything in there. But let's just say you do a 24 volt system. Okay, you wouldn't have a, well, I guess you might be able to find a 100-watt panel that puts out 24 volts for a 24-volt system. That one's set up for, wired for a 12-volt system. So it's nominal. It's coming out at about 18 something volts. So like I showed you that's what your charge controller needs in order to have enough pressure to push against the voltage that wants to come out of your batteries. You need a higher voltage than what's coming out to push back through. So what you have is a 12-volt system. But let's just say that you got a 100-watt panel and it put out 24, actually put out about 30 volts. Then you're only talking about 3 amps, 3 and a third amps or something like that. It's not going to put out a lot of ampage, which means you could do a 24-volt system. A 24-volt system is starting to crank up the voltage, and with the batteries, because you have a higher ampage, you really almost kind of want a breaker in there. You really do. So breakers or disconnects are interrupters for two purposes. One, it keeps you from working on a live system, keeps you safe, and it also allows you in that safety being able to turn off any section. And we'll go through these sections. The 4 system components. You get breakers in between each 4, which means 3 places for those breakers to be. And this is the first one. Now, you got 2 reasons. 1, to protect your equipment, and 2, to protect you. That's 2 main reasons. It allows you to work on different segments and still have your system working. So like, let's just say I had a panel get hit. We're going to go back to that. Have a panel get hit by a large hailstone and breaks the panel, and I need to replace this panel. But during the day, I still need to run my equipment, and I really don't want to shut the power off. So what I can do is I could open this up, and I could flip the breaker on this one string. So in essentially de-electrifying this section, then I could unbolt, take this off, put another one on, take the wiring, and reconnect the new panel into this system, and that breaker allows me to do that. See how that works? So breakers and disconnects are one of the most important aspects of your system that allows you safety and controllability of when and how you work on your system. So here we go. We'll talk about this one a little bit. All right, so I've got 2 strings of 3. So we already determined I've got, almost 93 volts, and then 93 volts, so it stays 93 volts, but we're adding ampage here. So that's going to give me 17 amps. All right, so as it comes into her, and for this particular moment, I'm not going to disassemble any of these. I'm just going to talk you through them. There are 2 breakers in here. Those 2 breakers are handling each string, okay? They are sized, or the breaker, and this is what we want to discuss about these breakers. These breakers need to be sized mathematically based on the limits. Now, hear me on this, based on the limits of your string. Hey, she was doing fine. He's been in a little mood. Midnight. Leave her alone. Kids, I tell you, when they get to roughhousing, sometimes you're going to have to, you know how it is. All right, so we've got 2 strings, and I need to make sure that these breakers are sized. Now I'm sizing this based on the amount of production that I need to meet my loads, okay, and the outgo. And we'll talk about sizing when we get into the panels themselves. But I need to size. We're going to talk about sizing on our breakers and disconnects. Disconnects are on-off switches, so there's no size to it, but they need to be rated for the maximum amount of power that you're going to have going through them. So, you know, you're talking 17 amps and you're talking 100-ish volts, okay? That tells you you're going to need something rated higher than that. Now, there's two breakers in here, and like I said, we're not going to look at them now, but they are rated for the maximum of what can go into my charge controller. We'll go in there in a minute, and we'll talk about that. So I could potentially add another panel, as we discussed. I can't go to 5 because that will exceed what my rating is on my charge controller, the one that's hanging on the wall. That will do a 60 amps, 150 volts. So I'm limited to 150 volts here. I'm also limited to 60 amps, but I've only got 17 amps coming in here, and I've only got, you know, 100 volts. So the breakers have to be sized for the limitations of that, because that saves that. So if I were to have, let's just say I went ahead and screwed up here and I threw 5 panels together, and that put me at 150 volts. Okay. Well, first off, the size breakers that they put in these are, there's just about an industry standard on these breakers, and they are 150 volt, 15 amp. That's what they put in. That's the standard size. That's 99% of you are going to probably use something very close to that. It's just because it's how this industry has standardized certain parts. So here's the thing. A little trick about these panels. The colder it gets, the more they function, the better they function. Let's just say I set up these panels and we do the math on it, and I put as many as I can, and you see that open circuit voltage is 38 volts. So 3 of them together, okay, 3 of these together is what, nearly 120. Okay, so if I put 4 of them together, I'm actually overvolting my string, because if I put 4 of them together, I have the potential in the right conditions to exceed that 150 volts. You hear what I'm saying? It's not likely going to happen. That only happens when you have a short circuit straight through the panels. Okay? But they're rated at that because there's this unique condition with the solar panels. And the solar panels, if they get really, really cold and the sun isn't directly on them, but it's starting to build up light, it has the tendency to build charge. And I have had this happen to me with 3 panels, and that's why I don't go above 3 in a string for this particular situation, because I don't want to have to reset the breaker in cold, very, very, very cold mornings when the sun pops up and all of a sudden I get a voltage surge. So you got those put together, you need to protect it. So that's what the 150 volts is, 150 volt breaker is. The breakers are 150 volt, 15 amp. Okay, now I'm not going to have 15 amps with one string. That's not going to happen. But my voltage may go up higher, and that might kick that breaker. Now, once you get in there and you've got the 2 of them, each string has its own breaker that separates the 2 strings. In the breakers, both breakers are separate until they come out. Once both strings have moved through a breakering point, they're combined into a little bus bar. That bus bar combines both currents into one current and 1 ampage. So now we're combined, and there are only, there's 3 wires that go through here, a ground, a positive, and a negative, and that positive and negative now is running at 93 volts and 17 amps. Got it? So we want breakers here. Now let's go in here and let's discuss the next 2 places that you're going to need. You're going to need your breakers. Like I said, for the purpose of this video, I'm not going to disassemble each one of these to show you the inside. It's more important about getting the concept. So on my wall, all of that is coming through that conduit and into here. Well, the positive and the negative are. And the positive and negative go into the terminal connections into the charge controller. And you can see it maxes out at 60 amps and 150 volts. There are other charge controllers that have different ratings. You have to match yours when you size your system. So right now I've got an input of 347 watts. There's 84.9 volts, and that you can see that bouncing around, and 4.3 amps to get that number. So this times this equals that number up there. You see where we're going? But this is going to output, it's going to convert this to a lower voltage multi-power point tracking. So it doesn't matter whether I got 2 panels or 3 panels or 4 panels. This is going to take it and it's going to give me the output I need, which is right now is at 26.5 volts. It should be a little higher, but we just went back into some clouds from where that sun was, so it's dropped off. This generally wants to sit around 27 volts when it's or 27, 26.9, 27, 27.1 when it's in float charge, and that's the maintenance charge that it puts. But sometimes, let's do this. Let me show you what we got here. Let's go to the battery menu, and I'm going to activate the equalization, and that's what this is, a maintenance for the batteries that it can do. So I'm going to exit that, and then I'm going to look down at it, and it's not there yet, but this number is going to go, you see it's now 26.8. It's starting to pump more into it. This number could actually go up to 32 volts, I think, is the highest setting, depending upon your kinds of batteries. So this can crank out quite a bit, and I've seen this number as high as 1500. I've never seen a full 1700 coming off my panels because there is resistance within the wiring getting here. Alright, so let me turn that off, because I don't need it. Oops. I don't need it doing that. So here's the thing. Suppose I need to work on my batteries under the table. There's not very good light there, so we're just going to look at the breakers. I have 3 breakers here, and this one, it's hard to read, is a 60 amp breaker. Why? Because I'm putting out 60 amps. Alright, and my battery's set for this. I'm matching my ampage. Alright, so it also handles up to, I think, 100 and I forget the rating. I'll have to clarify that before I say it. I don't want to say that. Alright, so there's 2 breakers that are turned on right here. There's a breaker between the charge controller and the batteries, so that if I have to, I can turn this off in order to work on the charge controller or the solar panels out there or the batteries. I am disconnecting between this component and the battery component. Then with those 2 big cables that come up here, one of them comes directly to the positive, goes directly to or goes to the, excuse me, the positive goes to the I'm sorry, the negative goes through the disconnect. The positive goes directly to the terminal on the inverter in order for it to be powered up. We disconnect on the negative side in this particular system, because if something's grounded out, you need to shut it off so that there's no potential continual circuit. So you shut off the negative, not the positive. You shut off the negative in this particular setup. It may not be that way for yours. Different systems are wired differently. But anyway, the point is this. We have a breaker between the charge controller and the batteries, and then we have another breaker between the batteries and the inverter. And each one of these is sized to handle the maximum of each component. Okay, so the maximum of this component, it doesn't want more than 250 amps. Because you got to remember, if we're going at a low voltage, in order to get the wattage and the current you need, you have to up the amps. And upping the amps is the reason why you have the much bigger cables in order to handle that much volume. And that's what current or watts is the volume of electrons that are flowing. So we will get into some more aspects of the breakery later, but for now, understanding the concept of why you need it is that you need it for your protection and the protection of the equipment, and that you're sizing your breakers to handle what the maximum load is of your equipment. So this breaker is sized for this equipment, and this breaker is sized for that equipment. If that makes sense. So when you're shopping for components, you've got to know what each one of those numbers means so that you're getting something that's the right size. Make sense? All right, that will end part 6, I think, of our Solar 101. We're just getting started into a bunch of it, but like I said, most of this is conceptual in function and knowing why you need to know this and what you need to know. We'll get into more of the details of how to size and so on and so forth here later, but the next string of videos are going to be on each component, and we'll talk about each component. We'll do a video strictly on the solar panels, we'll do a video strictly on the charge controllers, we'll do a video strictly on the batteries, and we'll do a video strictly on the inverters. And that concludes number 6. Talk to you soon.